Okay, so I am going to talk about modeling and stability analysis for a class of stochastic hybrid inclusions. So obviously Shankar and his students have been doing a lot of work on hybrid systems, including stochastic hybrid systems. I was a student of Shankar's, by the way, but was not working on hybrid systems at the time, so I came much later to the game. But here's a photo that I dug up from 1992. So I guess this was about 24 years ago. And so that makes Shankar about 36 at the time. One thing, by the way, that really stands out in my memory is, so Shankar got the Ekman Award when I was a graduate student, and it just shocked me to learn how young he was at the time, right? You have to be 35 or younger. And I really had no idea that he was that young. But there he is, looking young and good. And then on the left is Raja Kadiala, a classmate of mine who was here yesterday and works in industry. So it's a pleasure to be here and to be giving this talk and to be talking about something that, that Shankar has worked on extensively with his students. So the class of systems that I'm going to discuss is modeled formally in this particular form. So as a hybrid system, it combines flowing and jumping. And I'm going to focus, just for this talk, because it's short, on models where the randomness only appears in the jump equations. So there's no randomness in the flows. You can add randomness there, but we aren't as far along in the development of the results for those systems as we would like to be. So the state X evolves in a Euclidean space, but is constrained to a flow set C when it flows and should satisfy a differential inclusion when it flows. It's constrained to a jump set D when it jumps, and it satisfies a difference inclusion. And there's where the randomness shows up, that B plus is a placeholder for a sequence of IID random variables with a distribution mu. One of the prominent features of these models is that the solutions aren't necessarily unique. And most of the literature up till now on stochastic hybrid systems has insisted that solutions are unique. And for good reason, the analysis gets a lot more complicated in the non-uniqueness case. But we're interested in this situation for a variety of reasons. One motivation is that you can model systems with adversaries in a closed way by putting an inclusion down to represent all the possible directions that a disturbance might take, maybe subject to a certain magnitude constraint. You can also model with a single system all of the behaviors you get under an average dwell time switching mechanism, because you can write down an automaton that captures average dwell time switching. And then also, by the way, this framework, though it might not be obvious on the surface, captures the usual multiple mode hybrid systems with guard conditions, and this non-uniqueness covers the situation where you might be in a mode and two guard conditions are simultaneously satisfied, and so either jump is possible. So this talk, again being short, I'm just going to focus on Lyapunav functions and how they apply to these systems. And in particular, Krasovsky's LaSalle type stability theorems, which are going to seem pretty obvious on their surface, but are pretty difficult to establish for these systems. So one point then that I'd like to make is that Lyapunav conditions remain a vital analysis tool for certifying the behavior of stochastic hybrid inclusions. So one of the things that we were involved in early on for non-stochastic hybrid systems was showing that the Lyapunav function is actually a necessary condition for asymptotic stability in these systems. So I think maybe early on, the feeling was that these systems maybe were just too complicated to admit Lyapunav functions. But that turned out not to be the case, though finding them is still a challenge. Here I've written down conditions on a Lyapunav function to be not increasing in flow locations, maybe excluding some locations where we don't care so much about how the Lyapunav function is evolving, and looking at all the possible directions in which it can flow. That's the first inequality. And then in the stochastic case on the jump side, we're looking at the expected value not increasing. Again, at points in the jump set, but maybe excluding points that we don't care so much about. This type of inequality could be relevant for a couple of different stability-like properties. You're probably pretty familiar with the notion of asymptotic stability, maybe usually of equilibria, but for hybrid systems it makes a lot of sense to study this property for sets because very often variables don't settle down to a point. You might have logic variables oscillating through some periodic motion. You might have timer variables that keep resetting back to 0 and flowing. And you can talk about asymptotic stability and probability for the stochastic case. In that case, we would add to these Lyapunav conditions the assumption that V is positive definite with respect to A. That is, it's 0 in A and positive otherwise, and that it grows radially unbounded. Another interesting property that's especially relevant for stochastic systems, is not studied as much for the non-stochastic case, but is actually interesting there as well, is the notion of recurrence of a set. That is, that you keep coming back to this set over and over again. We usually talk about recurrence of open bounded sets. We usually talk about asymptotic stability of compact sets, and those then generate this set S that we exclude in terms of where we're looking at these Lyapunav conditions. And for recurrence, all that we care about is that V is non-negative, as well as being radially unbounded. So maybe to make a quick connection to Richard's talk, I don't study formal logic at all, but I broke out my phone to find the LaTeX commands for the square and the diamond, and this is the notion that. Pardon me? That's right. Yeah. Yeah, so phones are pretty impressive. But in any case, this is very similar to, or exactly, the always eventually behavior that Richard talked about. So, so following up on those Lyapunav conditions, it's worthwhile knowing. So this kind of feels funny to tell you about these results, because I think you're going to say, oh, well, you know, that's got to be true. And so it's obvious, and, you know, why are you telling us? But again, I guess the point is that it's really not so obvious, and we haven't figured out how to prove it yet for stochastic flows with inclusions that are involved. But for this class of systems, the invariance principle extends to this class of stochastic hybrid systems. There are some mild technical conditions that I'll tell you about on the next slide. But otherwise, there's an asymptotic stability theorem, which is to say, suppose that you know that this compact set is forward invariant almost surely, and you've got those Lyapunav conditions on the previous slide. Then the set A is uniformly globally asymptotically stable in probability. That's in italics because you'd want a formal definition, but I don't have time to give one. But I think you intuitively understand what it is from the picture on the previous slide. If and only if there does not exist a solution. Remember, solutions aren't necessarily unique. But there does not exist a solution. That's also in italics because that would also require a formal definition, but I don't have time. That almost surely keeps V equal to a non-zero constant on unbounded time domains. So if you can rule out that behavior, then you know that you're almost surely going to converge to A, and the Lyapunav function gives you the stability properties. Similarly, for recurrence, you can say the same kind of thing. If you've got those Lyapunav conditions on the previous slide, the set O is uniformly globally recurrent in probability. Again, you'd want a formal definition, but you kind of get the idea from the picture. If and only if there does not exist a solution that almost surely keeps V equal to a constant on unbounded time domains while remaining outside of O. And to piggyback on Aaron's metrics earlier today, I don't know if you can see this, but I've avoided giving definitions so that I could make my ratio 2/0. But on the other hand, there are no robots involved, so that brings me back to an indeterminate situation. In terms of the basic conditions, I said they are mild. They are simply that the flow set and the jump set are closed sets. The set-valued mappings F and G should be locally bounded. This just means that they map bounded sets to bounded sets. The F should be outer semi-continuous. That just means that it has a closed graph. And then you need some measurability properties on how G depends on the random input. If you're unfamiliar with measurability for set value mappings, which I was until I got into this field, I would encourage you to read Rockefeller and Vett's book, specifically chapter 14 in the variational analysis book. There's a very clear treatment of that material. But if you don't have these assumptions, then you can easily find examples where those somewhat obvious theorems of the previous page don't actually hold. So then, maybe just to wrap up with a single example where I can illustrate those theorems. Maybe not the most interesting example, but certainly an example that comes up a lot when you're teaching people the basics of hybrid systems would be a bouncing ball, where maybe you're going to make it stochastic. So we'll have flows that are corresponding to falling in a gravitational field. I've got height illustrated in the vertical direction and velocity in the horizontal direction in that picture. And then we'll have a reset of the velocity when we get to 0 height. And we can reset to maybe 2 different values, minus a times the velocity, where a is a number less than 1. And then maybe minus b times the velocity, where b is a number bigger than 1. If we had to deal with this on a worst case basis, we'd be in trouble because the b could keep being selected so that the solutions just grow in terms of energy at each jump. But if there's a probabilistic description, then there's a hope that we can deal with that positive or greater than 1 restitution coefficient. So you can assign a probability to getting A, which would be P, and 1 minus P for the probability. You can construct a Lyapunav function, which is the natural energy, maybe raised to some power. And that natural energy doesn't change during flows, so you're not getting strict negativity there, and so you're most likely going to need to depend on an invariance principle-like result. In terms of the jumps, you'll get that the expected value doesn't increase if you have this particular relationship between the P, the A, and the R. And you can see that when the P is 1, that's going to hold for free since A is less than 1. And then we can allow that P to move away from 0 and still have that expected value condition. And the fact that A is less than 1 guarantees that there's no complete solution, that is one with an unbounded time domain that keeps V equal to a non-zero constant almost surely. So therefore, these conditions are sufficient to, and in fact, sufficient to guarantee that the origin is uniformly globally asymptotically stable in probability. And just to play up the role that this R plays, and also the fact that we didn't really need to differentiate the Lyapunav function on the attractor, if you plug in A is equal to 0.5 and B is equal to 1.1, and you use R is equal to 1, which is just the normal natural energy, you need P to be greater than 0.22 to have this stability condition. But if you let R go towards 0, you can actually allow for smaller P's. In particular, you can get down to around 0.12. And then you could play the same game for the bouncing ball with a new update rule where not only do you reflect the velocity, but maybe there's an additive, maybe set valued disturbance that could take any value between 0 and C. You could play with the same Lyapunav function. And again, you won't increase during flows. During jumps, the expected value will decrease, but there'll be some constant D that you have to contend with that shows up that's related to the different numbers that show up in the problem. And because that lambda is less than 1 and V is radially unbounded, when the state's big enough, the expected value will be less than its value before the jump, and that'll mean that you'll have the Lyapunav condition satisfied, and so you'll have recurrence of a large enough open-bounded set. All right, so to wrap up, this talk just scratches the surface, really, of modeling issues in stability theory. I didn't have a lot of time to go into all the examples of systems that fit into the description, nor did I even have time to tell you what exactly a solution was, or to emphasize some of the causality issues that are central in Lyapunav functions being necessary and sufficient for these stability properties. There's a lot of interesting stuff to learn there. Some of the things that we have developed that I didn't talk about would be results based on Matrosov functions as an alternative to invariance principle type results. I'm not sure I was completely paying attention when Richard mentioned the box and the diamond and less than or equal to t, but my interpretation is that it's somehow related to something that we've also proved under these hybrid basic conditions, which is that if you have an open-bounded set being recurrent, that is, you come back to it infinitely often, then you can actually prove that from compact sets, there exists a uniform time that it takes to come back to the set. We've established some Converse Lyapunav theorems, some robustness results, that these properties are inherently robust under the hybrid basic conditions. In fact, all of those results are built upon a difficult mathematical result that has to do with how a sequence of solutions converges to something that's actually, again, a solution. There's still several important open questions that remain for these stochastic hybrid inclusions, most notably getting that core result for the case of stochastic flows and inclusions, and then from there, building this type of theory for that. But I'd like to wrap up by saying happy birthday, Shankar, and thank you for blazing a trail in this area for us. Yeah, there can be. Yeah. So there are sample paths that diverge, the sample path corresponding to the zero probability solution of drawing B's forever. But yeah, the probability is zero of that happening.
So I'm just wondering, though, in the box diamond, I think that the box diamond doesn't allow for, it has to be true for every single.
Well, yeah. So the box diamond is for deterministic systems. Yeah. But you can apply this idea, this recurrence idea, to deterministic systems. Yeah.
Well, this is the question for Richard was about thinking about stochastic versions of what he presented, which is quite interesting. So these are results in probability.
Yes, right. And so I didn't give the precise definitions, but the stability definitions, the attractivity definitions, the recurrence definitions are all expressed in terms of probabilities. And you can make the probability get closer and closer to 1 as you let the time get closer, and as the time grows unbounded, or as you start closer and closer to the attractor.
So it would be just a side comment, but it'd be really interesting, especially with the impact, the fact that Sam brought up earlier, there's non-uniqueness to post-impact states for robotic systems, right? So this would be really interesting to see if you can capture stability in that sense.
Yeah. This comes up a lot in hybrid systems, where you've got this scenario where multiple things can happen at once as the limit of them not happening at once, and this structure of setting up closed graphs for everything enables you to say that the limit of what you get not being simultaneous is included in the solution set that you get with them being simultaneous.
Okay. Is there any relationship between the recurrence relation and the behavior of invariant measure in terms of the subgroup of invariant measure if it converges to
There are certainly connections between recurrence and invariant measures, and I'm not fully prepared to answer your question, but that's certainly one of the primary motivations for people having studied recurrence in the past, was to link it to the characteristics of invariant measures. Yeah. I don't usually assume the type of irreducibility type assumptions that are associated with that, but yeah.